Hi everyone, I'm Caleb Koch, and I'll be telling you about our paper, The Sample Complexity of Smooth Boosting and the Tightness of the Hardcore Theorem. And this is joint work with Guy Blanc, Alex Hayderi, and Leon Tan. So this talk is going to be about two different topics. The first topic is boosting, which is a fundamental idea in machine learning. And the second topic is harness amplification, which is a fundamental idea in complexity theory. And although these two topics may seem unrelated to each other, as we'll see throughout the course of the talk, they're intimately connected. So let's start with the first topic, which is boosting in machine learning. So at a very high level, boosting is a way of upgrading a really bad learning algorithm into a really good learning algorithm. Okay, so let me elaborate on what I mean by that. So let's say that you have a learning algorithm of the following form. The learning algorithm learns an unknown Boolean function f, and the way it works is it gets a bunch of data, and the data is going to come in the form of labeled examples. So these are pairs x, f of x, where x is uniformly distributed. So the algorithm gets a bunch of these labeled examples, and then it does some computation, and it outputs a hypothesis h, and let's say that this hypothesis predicts f with accuracy 51%. So what that means is that over a random input, the probability that the label of f matches the label of the hypothesis is like 51%. And let me note that since we're dealing with binary classification tasks, the baseline accuracy here is 50%. If I just randomly guess the label of f, then I get 50% accuracy. So this learning algorithm does slightly better than random guessing. But there's a big downside here, which is that still this accuracy is not great. Ideally, we would like to construct a hypothesis that has very high accuracy, let's say accuracy 99%. So there's a challenge here, which is if I have a learning algorithm of this form, how might I upgrade it or convert it into one that gets high accuracy? And since this learning algorithm has low accuracy, we call it a weak learning algorithm. And our goal is to upgrade it to a strong learning algorithm, so one with high accuracy. So as I've set things up here, it's maybe not clear how you would do this. It doesn't seem like there's much room to do anything. So let me add an additional assumption, which is that this weak learning algorithm succeeds over any distribution, not just the uniform distribution, over inputs. Meaning, for any distribution that you give it, it outputs a hypothesis which has 51% accuracy with respect to that distribution over inputs. So now maybe there's something you could do where you can come up with a bunch of different distributions, run the learning algorithm on these different distributions, look at all of the outputs, all of the hypotheses that it creates, and then somehow combine them into a really good hypothesis. And it turns out that this does in fact work, and this is called boosting. So the idea is to come up with a sequence of distributions, let's say D1 through DT, and the boosting proceeds in T stages. And these are like adaptive stages. So you construct this distribution D1, you simulate the learner on the distribution D1, you look at the output, you then construct the distribution D2, simulate the weak learner, look at the output, come up with some distribution D3, and so on. And then after the T stages, you output a hypothesis, let's say capital H, which is really good at predicting f. So it gets accuracy, let's say 99% in predicting f. So this whole framework of upgrading this weak learning algorithm into a strong one is called boosting. And it originated with Shapiri and Freund in the early 90s. And let me mention that boosting has since evolved into a major influential paradigm within machine learning. Popular boosting algorithms such as AdaBoost are used a lot in practice and are very successful. And one interesting thing about boosting is that it emerged originally as a question in theory, a purely theoretical question. Can you upgrade a weak learning algorithm into a strong one? And then the algorithms that the theoreticians developed ended up having a huge influence in practice. Okay, so in spite of this success, I want to highlight two downsides of boosting as I've described it. So the first downside is maybe hopefully fairly clear from what I've said, which is that the weak learning algorithm must succeed on all distributions. And this is true even if your goal is to develop a strong learning algorithm just over the uniform distribution. So even if you want to predict H with high accuracy of the uniform distribution, you still need this very strong assumption that your weak learning algorithm succeeds on all distributions. The second downside, which I'm not going to go into too much detail on, is that existing boosting algorithms fail in the presence of noise. So ideally, it would be nice if all of our learning algorithms succeeded even when there's noise or corruptions in the data. And it turns out that for boosting algorithms such as AdaBoost, once the data is noisy, they no longer have the same performance that they do in the noiseless setting. And this kind of issue of noise tolerance has been observed ever since boosting was kind of first developed. Okay, so both of these downsides are addressed by a variant of boosting called smooth boosting, which was introduced by Servideo in 2003. So this variant works by having the boosting algorithm construct smooth distributions through the T stages, which it simulates the weak learner on. So a smooth boosting algorithm is one where each of the DI in the boosting stages are smooth distributions. So what's a smooth distribution? So I'm going to define it using a picture. So this is a smooth distribution. So what a smooth distribution is it's one where the weight of the distribution is kind of nice and spread out evenly throughout the domain. Another way of putting it is that the distribution has very high density in the domain, or the distribution doesn't place too much weight on any one input. Okay, so how does smooth boosting address the downsides that I mentioned above? Well, first, if we have a smooth boosting algorithm, well, now we only need a weak learning algorithm that succeeds on smooth distributions. So already that's kind of weakening that the initial assumption. Second, if we have a smooth boosting algorithm, it turns out that it generates a noise tolerant learner for the problem that we're trying to learn. So the intuition is that because each of these distributions are smooth, if some of the inputs were noisy, then that's not going to affect the output of the weak learner too much, because the distribution spreads its weight out across the entire input space. So that's kind of all I want to say intuitively about how it addresses noise tolerance, but suffice it to say that it can be shown that smooth boosting algorithms yield strong noise tolerant learning algorithms. Okay, so this brings me to the main question that we address in this work, which is, what is the sample complexity of boosting? So sample complexity is maybe the most fundamental resource in learning. How much data do you need to ensure that your learning algorithm succeeds? And specifically, we're interested in what is the sample complexity overhead of smooth boosting. So if I have a weak learner that uses some number of samples, how many more samples do I need in order to construct a strong learner? Okay, so let me go over briefly what existing smooth boosting algorithms guarantee. So existing smooth boosters have the following form. So they take a weak learner, which has accuracy, let's say half plus gamma, and think of gamma here as being very small. So in the initial example I had, gamma is like 1%. So the accuracy overall is like 51%. And let's say that this weak learner uses M samples to learn. Then the smooth boosting algorithm will upgrade this into a strong learning algorithm that achieves accuracy 99% and uses m over gamma squared samples. So the overhead here, the number of samples that you need, is like a multiplicative 1 over gamma squared factor relative to the sample complexity of the weak learner. Okay. Okay, so as we've seen, existing smooth boosters achieve a sample complexity overhead of 1 over gamma squared. And it's not too hard to show that you need some overhead in sample complexity. So there's an easy lower bound showing that you need at least an overhead of 1 over gamma squared to smooth boost. And our first main result is an improvement on this lower bound, showing that the sample complexity overhead of smooth boosting is 1 over gamma squared, matching the overhead of the existing smooth boosters. So this says that the sample complexity overhead of the existing smooth boosters is the best you could hope for. Okay, let me also mention that you can compare this result to the sample complexity overhead of regular boosting. So for regular boosting, it's not too hard to show that the sample complexity overhead is 1 over gamma, and this is matched by, there is both an upper bound and a lower bound. This is fairly easy to show. It follows via standard VC arguments, if you're familiar with that. If not, it's not a big deal. This says that kind of one of the key takeaways of our results is that there's a separation between regular boosting and smooth boosting in terms of the sample complexity overhead. Okay, so just so that we're all on the same page, let me formally state our main result. So the result is a construction. So we design a concept class C and show that this concept class C has 2 properties. The first property is an upper bound, saying that C can be learned to accuracy half plus gamma with m samples over any smooth distribution. And the second property is a lower bound, saying that if you want to learn C even over the uniform distribution to accuracy 99%, then you need m over gamma squared samples. So this says that if you want to do smooth boosting for this concept class, you need to incur an overhead of 1 over gamma squared in terms of sample complexity. Okay, so I'm going to transition now to the second topic of the talk, which is hardness amplification. Now, before I jump into hardness amplification, I want to zoom out and think about what boosting is at a very high level. Okay, so as we've seen, boosting is a way of connecting the following 2 tasks. If we have an algorithm A that learns to accuracy 51%, then boosting gives us an algorithm A prime which learns to accuracy 99%. Okay, now I want to compare this with hardness amplification. So hardness amplification at a very high level is a way of upgrading a kind of weak average case lower bound into a very strong average case lower bound. So what I mean by that is, suppose that we have a function which we know cannot be approximated to error 1% by polynomial size circuits. So this is a form of kind of mild inapproximability or mild average case hardness for a particular function f. And the idea of hardness amplification is to amplify this inapproximability to a very strong form of inapproximability. So if such a function exists, then with hardness amplification, you can derive the existence of a function f prime, which cannot be approximated with error 49% by polynomial size circuits. So you can't even do better than random guessing. And so when I compare the 2 ideas side by side like this, it kind of seems that they're related to each other, that they kind of have similar goals. And in fact, if you look at proofs of hardness amplification results, they all use boosting style arguments. So they all use an argument of the form, well, if you could kind of weakly approximate this function f prime with polynomial size circuits, then you can somehow boost these weak approximators into very strong approximators for the function f, which get error better than 1%. So, so in the contrapositive, this gives you hardness amplification. And this connection is not just kind of a surface level connection. It turns out that these two ideas are fundamentally related to each other, and this was first observed and explored by Clivens and Serradio in 2003. And in fact, using the connection between these two ideas, they were able to derive new results in both hardness amplification and in boosting. Okay, so let me briefly mention a foundational example of hardness amplification. And this is Yau's XOR lemma. So the idea of Yau's XOR lemma is if you have a function f which exhibits mild inapproximability, then you can form a function f prime which exhibits strong inapproximability by taking many independent copies of f and XORing them together. And this result has found many applications throughout complexity. It's a very fundamental result and an important example of hardness amplification. So I'm not going to go into more detail about Yau's XOR lemma itself, but I want to talk about one of the main ideas that goes into the proof of Yau's XOR lemma, and this is Impagliazzo's hardcore theorem. So the hardcore theorem is also itself a cornerstone result in complexity theory. It's been called one of the bits of magic of complexity theory, and our second result pertains to this theorem. So, what does the hardcore theorem say? It says the following. Suppose that I have a function that exhibits mild inapproximability in the sense that I mentioned before. So f cannot be approximated with error 1%, let's say by size s circuits. So what does this mean? So this means that if I take a circuit, let's say C1, which is size s, then it's going to have some patch of errors in the input domain, and the size of this patch is going to be at least 1% of the entire input domain. So maybe it's this circle here. And maybe, if I don't know anything else about this theorem, I might expect that if I look at a different circuit of size s, maybe C2 here, it'll have some different patch of errors that it makes, and that there's no relation amongst these patches of errors. And if I look at a third circuit of size s, it has its own patch of errors somewhere else in the input domain. So the surprising thing about the hardcore theorem is it says that there's a single set of inputs which is simultaneously hard for all circuits. So this is called the hardcore set, and it's kind of a patch of inputs which is like impossibly hard, in the sense that over this hardcore set, f exhibits a very strong form of inapproximability. So over the hardcore set, f cannot be approximated even within error half minus gamma by size s prime circuits, so you can't do much better than random guessing. So the key conceptual idea of the proof of the theorem is to use boosting. So how does it work? So suppose, for contradiction, that the theorem were false. Then what that means is that for every candidate hardcore set, I can actually get a weak approximator for f. And using boosting style arguments, you can kind of take many of these weak approximators for different for many different candidate hardcore sets and stitch them together to form a very strong approximator for f over the entire input domain. And so then stated in the contrapositive, we get that if f exhibits mild inapproximability, then there must exist a hardcore set. Okay, so I want to highlight a downside of the hardcore theorem, which is the following. So we start with mild inapproximability against size s circuits. However, we end up with strong inapproximability against size s prime circuits, where s prime is much smaller than s. So ideally, if we start with a lower bound against size S circuits, we would like to get a lower bound against size S circuits as well. But unfortunately, the theorem only obtains hardness against smaller size circuits. And in particular, I can say exactly how small S prime has to be. So if you want to achieve half minus gamma in approximability, then S prime has to be a factor gamma squared smaller than S. And this gamma squared, it's not merely a coincidence that it looks very similar to the gamma squared that we got in weak boosting. This is exactly a byproduct of the fact that the proof uses boosting style arguments. And in fact, this size loss is kind of a byproduct of using boosting style proofs, because the way the proof works is it takes smaller circuits which weakly approximate the function over hardcore sets, and then it stitches them together into a much bigger circuit which more strongly approximates F over the entire input domain. So any boosting style argument is going to incur some size loss. So a very natural question here, which has been asked in the literature by complexity theorists, is this size loss necessary? Maybe there's a different proof of the hardcore theorem that doesn't use boosting style arguments and obtains less of a size loss, or maybe even no size loss. Let me mention that another motivation for this question is that if you could improve the hardcore theorem, the size loss in the hardcore theorem, then it would have immediate implications for Gauss XOR lemma, which would be a breakthrough result. So our second main result is that actually the size loss is necessary, and in fact the hardcore theorem requires a size loss of a factor of gamma squared times S. Okay, let me briefly mention a word about the main proof idea for our second result. So the main construction is a randomized construction, and it works as follows. So we take in IID random Boolean functions, f1 through fn, and we compose them with the majority function. And we show that this construction satisfies two key properties. So the first property is a circuit lower bound, saying that with high probability over the choice of f1 through fn, no size S circuit can approximate big F with error 1%. So this says that big F exhibits mild inapproximability, which is the starting assumption of the hardcore theorem. And then the second property is an upper bound, saying that for every choice of f1 through fn and every candidate hardcore set, there is a much smaller circuit which weakly approximates big F over the candidate hardcore set. So this says that any proof of the hardcore theorem must incur a size loss of gamma squared times S. Okay, so zooming back out, I want to briefly recap our results and mention a few key takeaways. So our first result said at a high level that smooth boosting requires a large overhead in sample complexity. And the key takeaways for this result are that existing smooth boosting algorithms are optimal in terms of their sample complexity overhead. And also we saw that this result gives the first separation of smooth boosting from regular boosting in terms of the sample complexity overhead. Okay, our second result is that the hardcore theorem requires a large loss in circuit size. So this result says that the size loss that the hardcore theorem currently has is optimal, and relatedly, the boosting style proofs of the hardcore theorem are tight. Okay, let me briefly mention one future direction for follow-up work. So I mentioned Gauss XOR lemma, and similar to the hardcore theorem, a downside of the XOR lemma is that all known proofs of it also incur a size loss in circuit size. And in fact, the reason for this is that the hardcore theorem is used in proving Gauss XOR lemma. So in light of our result, this says that any proof of Yau's XOR lemma which goes through the hardcore theorem must incur a size loss. But maybe there's a different way of proving Gauss' XOR lemma which doesn't go through the hardcore theorem and doesn't incur a size loss. There's a very natural question here of whether this size loss is necessary. And this is a question that has been the subject of a lot of study, but still there's no unconditional results saying that the size loss is necessary or not. So in light of our second main result, a very natural question is, can you unconditionally show that the size loss is necessary in Yau's XOR lemma? Okay, that's it. Thanks for listening.